This will include a review of basic diesel combustion as it relates to exhaust emissions. Components of the exhaust gas recirculation system will be introduced, and the operation of each component will be discussed. Finally, the effects of exhaust gas recirculation on engine components will also be examined. Simply stated, the exhaust gas recirculation system takes a portion of the exhaust gas and returns it to the combustion chamber. To help understand how this reduces harmful emissions, let's first review some of the principles of diesel combustion. In a diesel engine, combustion occurs when fuel is injected into a cylinder containing air under high pressure and temperature. The rapidly burned fuel releases a large amount of heat energy. The release of heat energy drastically increases the pressure in the cylinder. This increased pressure drives the piston downward. This transfer of heat energy to mechanical energy makes it possible to power a truck, operate a generator, or perform countless other jobs Cummins engines are designed to do. The more oxygen available for combustion, the higher the combustion efficiency. 1 pound of fuel needs approximately 20 pounds of air to burn efficiently. Heat is produced during the compression stroke. As the air in the cylinder is compressed, the air molecules rub against each other, creating friction. Friction raises the temperature of the air to the point that when the fuel is injected into the cylinder, the mixture is ignited and begins to burn. Fuel, the third element necessary for combustion, is comprised almost entirely of combinations of hydrogen and carbon. Fuels differ in their ratio of hydrogen to carbon. These variations are commonly referred to as hydrocarbons. Previous approaches of emission control are not capable of meeting the new requirements. The next viable step in reducing peak combustion temperatures and therefore reducing emissions is to cool some of the exhaust gas, mix it with fresh intake air, and move this mixture into the combustion chamber. This process is known as exhaust gas recirculation, or EGR. The mixture of recirculated exhaust gas and fresh intake air is referred to as the charge air. The extra exhaust gas in the charge air is inert. This means that it has virtually no oxygen in it, therefore it will not support combustion. Also, some of the heat energy during combustion is absorbed by the inert exhaust gas instead of the fresh air, thereby reducing peak combustion temperature. This reduces the formation of NOx while minimizing the use of retarded timing. Pressure inside the exhaust manifold is increased. This is accomplished through the use of a variable geometry turbocharger, an exhaust throttle orifice, or other restrictions. The recirculated exhaust gas enters the water-cooled EGR cooler from the exhaust manifold, where its temperature is reduced. The cooled gas then continues to flow through the exhaust tubing to the EGR valve. When commanded to do so, the EGR valve opens and allows more exhaust gas to flow. The gas then flows through the EGR connection tubing toward the intake air inlet. On the intake side of the engine, the recirculated exhaust gas enters an inlet mixer. At this point, the compressed fresh intake air coming from the turbo is combined with the recirculated exhaust gas to form the charge air for combustion. This charge air then enters the intake manifold and then the combustion cylinders. The sliding nozzle inside of the turbine housing adjusts to vary the turbine volute exit area. This action creates the increased back pressure in the exhaust manifold to force some of the exhaust gas through the EGR valve when it opens. The sliding nozzle is adjusted by the VG actuator. With the nozzle ring fully closed, the turbine volute exit area is at its minimum. This creates the maximum exhaust manifold pressure. Turbocharger shaft speed and boost pressure are at their highest. With the nozzle ring in the fully open position, the turbine volute exit area is at its maximum. This creates the minimum exhaust manifold pressure. Turbocharger shaft speed and boost are at their lowest. The sliding nozzle position is infinitely variable between open and closed.